Hello, my friend, and welcome to Orbital Dreams. The Big Bang is usually imagined as a giant blast, but that picture is almost completely wrong. The universe didn't explode into empty space. Space itself was changing, stretching, cooling, and slowly becoming the reality we now live inside. Tonight, we'll follow that story backward toward the first moments, before galaxies, before atoms, before light could travel freely, and before time itself becomes easy to understand. This is a calm journey into one of the deepest questions science can ask. Relax, forget your struggles and worries, and let gentle scientific wonder carry you to peaceful and restorative sleep. Chapter 1. The Question of the First Moment. This journey begins with one of the most fundamental and exciting questions science can ask: whether time itself had a beginning, and what the universe was like when reality first became possible. At first, the question sounds simple. We are used to beginnings. A day begins when the sun rises. A story begins with its first sentence. A life begins with a first breath. So it feels natural to ask the same thing about everything. When did the universe begin? What was the first moment? What happened before stars, before planets, before atoms, before light could travel freely through space? But the deeper we look, the stranger the question becomes. The beginning of the universe is not just another event inside time, like the lighting of a match or the birth of a star. It may be the place where time, space, matter, energy, and the rules that connect them were all pressed into a state so extreme that ordinary language begins to fail. To ask about the first moment is not only to ask what happened long ago. It is to ask what time is, what it means for something to happen, and whether the universe can have a boundary that is not a wall, but a limit of understanding. Modern cosmology begins with a remarkable discovery. The universe is not static. Galaxies on very large scales are moving away from one another, not because they are flying through space from a central explosion, but because space itself is expanding. The distance between distant galaxies grows as the fabric of the universe stretches. When scientists run that expansion backward in thought, the universe becomes smaller, hotter, and denser. Stars have not yet formed. Atoms cannot yet survive. Matter becomes a dense, glowing plasma. Farther back still, even familiar particles and forces existed under conditions that are difficult to recreate, even in the most powerful experiments. This backward journey leads us toward what we call the Big Bang. But the name can be misleading. It was not an explosion that happened at one location in an empty space around it. There was no outside room into which the universe expanded, at least not in the usual sense. The Big Bang is better understood as the earliest hot, dense state from which our observable universe evolved. Every region of space we can see today was once part of that incredibly compressed beginning. The universe was not expanding into darkness. Space itself was changing. This is why the first moment is so difficult to picture. Our imagination likes scenes, a point of light in a black void, a spark, a blast, a shell of matter flying outward. But those images quietly assume that space already exists, that time is already passing, and that there is a stage on which the event can unfold. The early universe asks us to remove the stage itself. It asks us to imagine not a thing inside space, but the origin of the conditions that make space meaningful. And then there is the question of time. In everyday life, time feels like a river. We remember the past, experience the present, and move toward the future. But in physics, time is more than a feeling. It is woven into the structure of the universe. In Einstein's theory of general relativity, space and time form a connected fabric called space-time. Gravity is not only a force pulling objects together, it is also the curvature of space-time caused by matter and energy. Massive objects shape time as well as space. Clocks run differently depending on gravity and motion. This means time is not an invisible universal background that ticks the same way everywhere. It is part of the physical universe itself. That idea changes the question completely. If time is part of the universe, then asking what happened before the universe may be like asking what is north of the North Pole. The words seem meaningful at first, but they may point beyond the place where the concept applies. If time began with the universe, then there may not be a before in the ordinary sense. Not because something is being hidden from us, but because before depends on time already existing. Still, scientists do not simply stop there. The edge of current knowledge is not a wall of silence. It is a frontier. General relativity describes gravity and the large-scale evolution of the universe with extraordinary success. Quantum theory describes matter and energy at the smallest scales with extraordinary success. But when we try to describe the very earliest universe, both kinds of physics become necessary at once. The universe was enormously dense, so gravity mattered deeply. It was also incredibly small in the sense that quantum effects could not be ignored. Yet we do not currently have a complete, confirmed theory that joins gravity and quantum mechanics into one clear description of that first state. Because of this, scientists can speak with strong confidence about many things that happened after the earliest mysterious boundary. They can describe how the universe cooled, how particles formed, how light eventually moved freely, and how small differences in density grew into galaxies. They can read traces of the early universe in the faint background glow that still fills space, a kind of ancient afterlight from a time when the cosmos became transparent. They can measure the expansion of the universe and study the abundance of light elements forged in the early heat. These observations give the Big Bang model its power. It is not just a story. It is a framework supported by evidence from the sky. But the exact first moment remains more uncertain. If we follow the equations of general relativity backward without adding new physics, they point toward a singularity, a state where density and curvature become infinite. But many physicists do not treat this as a literal object or a proven physical condition. Instead, it may be a sign that the theory has been pushed beyond its range. When a map leads into a blank region, the blankness does not mean there is nothing there. It means the map is incomplete. In the same way, the singularity may be telling us that our current description breaks down before we reach the true beginning. This is where the mystery becomes especially beautiful. The first moment may not have been a sharp instant in the way we imagine. It may have been a transition from an earlier physical state we don't yet understand. It may have involved a quantum origin, a bounce from a previous contracting phase, or a boundary where asking for an earlier time loses meaning. These ideas are explored carefully, but none has yet replaced the standard picture with confirmed certainty. The honest scientific position is both powerful and humble. We know a great deal about the young universe, but we do not yet know the deepest nature of its beginning. For an average human mind, this can feel almost too large to hold. We live among objects, distances, schedules, memories, and days. Our brains evolved to understand falling stones, changing weather, faces, footsteps, and seasons. They did not evolve to intuitively grasp space-time emerging from an extreme early state, so it is not a failure of imagination if the beginning of time feels strange. It should feel strange. It is one of the rare questions where science does not make the universe smaller. It makes the ordinary world feel more astonishing. When you look around at a quiet room, a window, a hand resting on a blanket, or the soft darkness behind closed eyes, everything appears stable and familiar. But every familiar thing is connected to that early mystery. The atoms in the air, the light from a lamp, the warmth of your body, the earth beneath you, and the stars above you all belong to a universe that has been unfolding from a hot, dense beginning for billions of years. The first moment is not only far away in time, it is beneath every present moment. It is written into the expansion of space, the structure of matter, and the fact that there is something here to notice anything at all. This is why the beginning of time is not just an ancient event. It is the opening question behind all other cosmic questions. Before we can ask how galaxies formed, how stars were born, how planets cooled, or how life appeared, we must first ask how the universe became a place where formation, change, and history could happen. Time is the condition that allows a story to exist. Without time, there is no before and after, no cooling, no growth, no memory, no waiting, no becoming. And yet, even with all this mystery, the search is not chaotic. It is careful, patient, and grounded. Scientists compare ideas with observations. They test predictions against the ancient light of the universe, the motion of galaxies, and the patterns left behind in matter. They accept uncertainty where uncertainty is real. That is part of what makes the subject so calming in its own way. The universe does not need us to pretend we know everything. It invites us to look honestly, to follow evidence as far as it can take us, and to rest gently at the edge of what remains unknown. So as this journey begins, we do not need to imagine the first moment as a violent flash or a sudden answer. It may be better to imagine it as a quiet horizon in thought. The place where our best physics approaches the origin of space and time, and where the universe becomes both more mysterious and more understandable at once. For now, you can let that question remain open. You do not need to solve the beginning of time tonight. You can simply rest with the thought that everything you know, every worry from the day, every small sound in the room belongs to a universe still unfolding from its deepest mystery, slowly and silently carrying you with it. Chapter 2. The universe expands backward. To understand the beginning of time, the first step is not to imagine an explosion, but to notice something quieter and stranger. The universe, on its largest scales, is stretching. When we look at the night sky with our eyes alone, the universe seems still. Stars appear almost fixed, like distant points held in place against darkness. The moon changes position from night to night, and the planets wander slowly among the constellations, but the deeper universe seems calm and motionless. This impression is natural because human life is brief compared with cosmic time. Galaxies are so far away that their movement cannot be watched directly in the way we watch a cloud drift across the sky. But light carries information. It does not only show us that distant objects exist, it also tells us how they are moving, what they are made of, and how the space between us and them has changed during the light's journey. When astronomers study light from distant galaxies, they find a pattern that is one of the most important clues in modern science. The light from most distant galaxies is stretched toward redder wavelengths. This effect is called redshift. In simple terms, the light has been lengthened while traveling across expanding space. A helpful way to imagine this is to think of a wave drawn on an elastic sheet. If the sheet is stretched, the wave drawn on it stretches too. In the universe, light behaves in a related way. As space expands, the wavelength of light traveling through that space also expands. Blue light can become less blue. Visible light can shift toward infrared. Radiation that began as intense early light can eventually become a faint microwave glow. Redshift is not just a change in color. It is a record of cosmic expansion written into the light itself. The farther away a galaxy is, the more strongly its light is usually redshifted. This does not mean every galaxy moves in perfect order. Nearby galaxies can be pulled by local gravity. Some even move toward us, including the Andromeda Galaxy, because it is gravitationally bound to our local group. But across enormous distances beyond the smaller motions caused by local gravity, a clear pattern appears. Distant galaxies are separating from us and from one another in a way that shows the universe itself is expanding. Once scientists understood that the universe is expanding, a profound question followed naturally. If space is stretching today, what happens if we mentally reverse that stretching? Imagine a film of the universe played backward. Galaxies that are now separated by vast distances would move closer together. The space between them would shrink. The universe would become denser. Radiation would become more compressed. The temperature of the cosmos would rise. The farther back we go, the less the universe resembles the quiet star-filled darkness we know today. This backward reasoning does not mean galaxies once flew out from a single central point. There is no known cosmic center from which everything escaped. Instead, every large region of space was once closer to every other large region of space. The expansion is not like fragments spreading through empty air. It is more like distances inside the universe growing over time. If the expansion is reversed, those distances decrease everywhere. The whole observable universe becomes a hotter, denser version of itself. This idea can feel difficult because our minds are used to motion through space. If a car drives away, it begins somewhere and moves somewhere else. If sparks fly from a fire, they travel through the air around them. But cosmic expansion is different. Galaxies are not simply racing through pre-existing emptiness. On the largest scales, the space between galaxy groups is increasing. The galaxies are carried apart as the geometry of the universe changes. A classic analogy is the surface of a balloon being inflated. Dots on the balloon's surface move farther apart as the surface stretches. No dot on the surface has to be the center of expansion. From the point of view of any dot, most other dots appear to move away. The analogy is not perfect because the universe is not literally the surface of a balloon, and real space has 3 dimensions. But it helps with one key idea. Expansion can happen everywhere without needing a central point inside the universe. When we follow expansion backward, the universe becomes more crowded with energy. Today, space feels cold and thin. Matter is gathered into galaxies, stars, planets, and clouds of gas, separated by enormous emptiness. But in the young universe, matter and radiation were packed much more tightly together. Light could not travel freely for a long time because charged particles scattered it again and again. The universe was more like a glowing fog than a transparent night sky. Later, as it expanded and cooled, matter became less energetic, particles could combine into atoms, and light could move across space more freely. Much later still, gravity gathered matter into the first stars and galaxies. Expansion also explains why the past was hotter. This may seem surprising at first. We usually think of expansion as simply making something larger. But when energy is spread through a larger volume, the temperature tends to fall. A compressed gas warms when squeezed and cools when allowed to expand. The early universe was not exactly an ordinary gas in a container, but the broad idea helps. As the universe expanded, its contents cooled. So when we reverse that process, we move toward a hotter and denser past. This backward path is not just a guess. It is supported by several kinds of evidence that fit together. The redshifts of galaxies show expansion. The faint, ancient background radiation shows that the universe was once hot and dense enough to glow everywhere. The amounts of simple elements, such as hydrogen and helium, match what we expect from an early period of intense heat where light atomic nuclei could form. The large-scale distribution of galaxies also carries traces of early differences in density that later grew under gravity. These clues support one another, giving scientists confidence that the universe truly evolved from a much hotter and denser state. Still, playing the cosmic film backward must be done carefully. We can trace the universe through well-understood stages, but not all the way to a perfectly certain first frame. Physics works beautifully across much of cosmic history, but the earliest moments demand conditions where current theories become incomplete. Expansion leads us backward toward an extreme beginning, but it does not automatically answer every question about that beginning. It tells us the universe was hotter and denser. It tells us that galaxies formed from earlier structure. It tells us that cosmic history has direction. But at the deepest edge, where density and energy become unimaginably high, known equations begin to lose their full authority. There is another subtle point. The expansion of the universe does not mean that everything inside the universe is expanding. Your body is not stretching with cosmic expansion. The Earth is not growing larger. The solar system is not being pulled apart by the general expansion of space. Galaxies themselves are held together by gravity. Atoms are held together by electromagnetic forces. On smaller scales, these forces are much stronger than the effect of cosmic expansion. Expansion becomes obvious only across the immense distances between galaxy clusters and superclusters, where local binding is weaker and the overall evolution of space can be seen. And yet, that background motion changes everything. It means the universe has an age. It means the sky is not just a collection of objects, but a record of change. Distant galaxies are not only far away in space. Because light takes time to travel, they are also seen as they were long ago. Looking outward is also looking backward. The deeper we look, the earlier the universe appears. The sky becomes a kind of time machine, not because we travel into the past, but because ancient light is only now arriving. The universe does not tell its story in words. It tells it through stretched light, ancient radiation, elemental abundance, and the slow architecture of galaxies. From these clues, scientists reconstruct a vast history. They learn that the darkness between stars was once filled with heat. They learn that empty-looking space is part of a changing cosmic fabric. They learn that the present universe is not the first form reality took, but one stage in a long unfolding. So when we say the universe expands backward, we are describing more than a mental trick. We are describing a way of reading time from space itself. The farther apart galaxies are today, the closer together they were in the past. The colder the universe becomes as it expands, the hotter it must have been before. The faint signals arriving from great distances are not merely distant signals. They are memories of a younger cosmos. And as we rest with this idea, the beginning of time becomes a little less like an impossible wall and a little more like a horizon we can approach step by step. We do not see the first moment directly, but we see the trail it left behind. The universe is still expanding now quietly everywhere on the largest scales, carrying galaxies into wider separation and carrying us forward with them. For tonight, you can let that thought soften rather than overwhelm you. The same expanding universe that once held everything closer together now holds this quiet moment too. Nothing needs to be rushed. The cosmos has been unfolding for longer than the mind can easily hold. And for now, it is enough simply to breathe, listen, and drift with it. Chapter 3. The Big Bang was not an explosion in space. The most important thing to understand about the Big Bang is that it was not a blast in the dark, but a transformation of space itself. The phrase Big Bang is powerful, but it can also be misleading. It makes the beginning of the universe sound like a firework, a bomb, or a star bursting inside an empty room. In that picture, there is a central point where everything starts and matter flies outward into a vast darkness that was already waiting. It is an image that feels natural because it matches the kinds of explosions we know from ordinary life. Something small becomes something larger. Pieces move away from a center. Empty space surrounds the event. But the universe did not begin like a firework inside space. According to the modern scientific picture, the Big Bang describes an early state in which the universe was extremely hot, extremely dense, and expanding. It does not describe matter exploding into a pre-existing void. It describes the expansion of space itself, along with the cooling and changing of everything inside it. The difference may sound subtle at first, but it changes the entire meaning of the story. An explosion has a location. It happens somewhere. If a star explodes, it explodes in a region of space, and the material spreads outward into the space around it. If a volcano erupts, the ash and gas move through the atmosphere above the ground. But the Big Bang was not an event with a location inside a larger environment. It was not here rather than there. It happened everywhere that later became the universe we can observe. Every distant galaxy, every empty region between galaxies, every direction in the sky traces back to that same hotter and denser early condition. This means there is no special place in the universe that marks the center of the Big Bang. From our point of view, distant galaxies appear to recede in many directions, but that does not mean we are at the center. Observers in another distant galaxy would see a similar pattern, with galaxies moving away from them as well. The expansion is not centered on Earth or on the Milky Way or on any hidden point beyond our view. It is built into the geometry of space on the largest scales. A useful image is rising bread dough with raisins inside it. As the dough expands, the raisins become farther apart. No raisin has to be the center of the expansion. From the viewpoint of each raisin, many of the others move away. This analogy is not perfect because galaxies are not raisins and space is not dough, but it helps correct the most important misconception. The expansion does not require a central blast. It is the distance between distant objects increasing because the space between them changes. Another way to think about it is to imagine every ruler in the universe becoming longer when used across vast cosmic distances. The objects themselves do not need to fly through space at enormous speeds in the ordinary sense. Instead, the scale of space changes. Distances grow. Light traveling through that growing space is stretched. The universe becomes cooler and less dense as it expands. If we look backward in time, we find the opposite. Distances shrink, wavelengths shorten, temperatures rise, and matter becomes more tightly packed. But even this backward picture needs care. It is tempting to imagine the universe shrinking down into a tiny ball floating in nothingness. That image also smuggles in an outside view. It asks us to stand somewhere beyond the universe and watch it become smaller. Yet science does not require such an outside location. The early universe was not necessarily a tiny ball surrounded by empty space. What became our observable universe was once compressed into a much smaller, hotter, denser state. But the whole universe may be larger than the part we can observe, and it may even be infinite. If space is infinite today, then it may also have been infinite in the early universe, only with everything much more densely packed everywhere. This is one of the strangest ideas in cosmology. An infinite universe can expand without expanding into anything. Infinity does not need more room outside itself. Instead, distances within it can grow. If the universe is finite, it still does not need to have an edge, like the edge of a table. A curved space can be finite in volume, without having a boundary you could reach and fall over. Our observations show that the part of the universe we can measure is very close to flat on large scales, but the full shape and size of the entire universe remain open questions. What matters for the Big Bang is that expansion describes the behavior of space itself, not debris flying away from a central point. The name also creates another confusion. It sounds like the Big Bang explains the absolute beginning of everything. In common speech, people often use it that way. But in careful science, the Big Bang model describes the universe evolving from an early hot, dense state. It is extremely successful at explaining how the universe expanded, cooled, formed simple atomic nuclei, later became transparent to light, and eventually developed the structures we see today. It does not by itself give a complete answer to why there was a universe at all, or what happened at the deepest boundary of time. Those questions reach into the limits of known physics. So the Big Bang is not a simple creation scene. It is a scientific model of cosmic evolution. It tells us that the universe has not always looked like it does now. There was a time before stars, before galaxies, before planets, before chemistry as we know it. The universe began its observable history in a state so hot that matter could not form atoms. Particles and radiation interacted constantly. Space was filled not with quiet darkness, but with an intense, dense, glowing mixture of energy and matter. As expansion continued, the universe cooled. Cooling allowed new forms of structure to appear. At first, the universe was too energetic for stable atoms. Later, atomic nuclei could persist. Later still, electrons could join nuclei to form neutral atoms. Once that happened, light was no longer scattered constantly by charged particles, and the universe became transparent. Much later, gravity slowly gathered matter into clouds, stars, galaxies, and clusters. The calm night sky is therefore not the opposite of the Big Bang. It is one of its long-term results. This helps us understand why the Big Bang was not a moment of disorder in the simple sense. It was an early state from which order and structure could gradually emerge. The universe expanded and cooled, but gravity amplified tiny differences in density. Regions with slightly more matter pulled in more matter over time. The universe became clumpy, galaxies formed, stars ignited, heavy elements were forged inside stars and spread by stellar explosions. Planets assembled around later generations of stars. Eventually, in at least one small region, chemistry became complex enough for life. All of that was possible because the early universe had both uniformity and tiny imperfections. If it had been perfectly smooth, there would have been no seeds for galaxies. If it had been too chaotic, the large-scale universe might not have developed the delicate structure we observe. The Big Bang picture, therefore, includes not only expansion, but also the origin of cosmic structure. It links the largest patterns in the sky to tiny variations in the young universe. There is also no sound in the ordinary sense implied by the word bang. Sound needs a medium, such as air or water, and it travels as pressure waves through that medium. The early universe did contain waves in its dense plasma, but they were not a bang heard from outside. There was no outside ear, no surrounding air, no silent room into which the sound expanded. The word survives because it is memorable, not because it accurately describes a noise. The more accurate image is quieter and more profound. Imagine not an explosion, but a universe whose distances are changing. Imagine a cosmos that begins its observable story as hot, dense, and nearly uniform, then expands, cools, and slowly becomes transparent, structured, and complex. Imagine every direction in the sky pointing back, not to a central blast, but to an earlier condition shared by all visible regions of space. The Big Bang is not a place, it is a phase in the history of the whole universe. This view can feel less dramatic than the idea of a cosmic explosion, but it is actually far more astonishing. An explosion is familiar, expanding space is not. A blast has a center. The universe does not need one. An explosion happens inside time and space. The early universe brings us close to questions about how time and space themselves behave under extreme conditions. Instead of a flash in the void, we are dealing with the evolution of the void, the light, the matter, and the rules that allowed distance and history to exist. And so, as we continue this journey, it is worth gently letting go of the firework image. The beginning was not a spark thrown into darkness. It was the universe in a younger, hotter, denser form, carrying within it the conditions from which everything familiar would slowly arise. The darkness between stars, the atoms in your body, and the quiet space around you are not separate from that beginning. They are its later expression. For now, allow that thought to settle softly. The universe did not need to explode outward to become vast. It only needed time, expansion, cooling, and the patient unfolding of structure. And tonight, there is nothing you need to force or solve. You can simply rest inside a cosmos that has been opening gently in every direction for longer than ordinary thought can hold. Chapter 4. The first fraction of a second. The first fraction of a second after the universe entered its hot expanding history may be the most intense transformation reality has ever undergone. In ordinary life, a fraction of a second is almost nothing. It is too brief for a thought to fully form, too brief for a sound to become a word, too brief for the eye to notice much more than a flash. But in the earliest universe, a fraction of a second was not empty time. It was an entire age of change. Conditions shifted so rapidly that the universe passed through states more extreme than anything that exists naturally in the cosmos today. At this stage, the universe was not a place filled with stars, planets, dust, or even atoms. Those structures belonged to a much later future. The early universe was a dense, searing environment of energy and particles, expanding and cooling with astonishing speed. Space was not empty between objects because the familiar objects had not yet formed. Instead, the universe was filled everywhere with a hot, restless mixture in which matter and radiation were constantly interacting. To understand this period, it helps to set aside the idea of solid things. The universe was not made of stable pieces arranged in space like grains of sand. It was more like an ocean of fields and particles, where energy could transform into particle pairs, and particle pairs could transform back into energy. At very high temperatures, the boundary between matter and energy becomes less familiar. Particles can appear through energetic interactions, vanish through collisions with their opposites, and remain in a kind of violent balance as long as the universe stays hot enough. This does not mean particles appeared from nothing in a magical sense. It means that energy, under the rules of quantum physics, can take the form of particles when conditions allow. In the early universe, conditions were so energetic that many particle reactions happened constantly. The cosmos was like a furnace, but not a furnace sitting somewhere in space. It was space itself filled with heat, radiation, and rapidly changing forms of matter. During the earliest part of this story, our confidence becomes limited. The closer we move toward the beginning, the more we need a theory that can describe gravity and quantum physics together. Since that complete theory has not yet been confirmed, scientists speak carefully about the most extreme boundary. But after that earliest uncertainty, the universe enters stages where known physics can guide us more clearly. The first fraction of a second is still strange, but not entirely beyond reach. As the universe expanded, it cooled. Cooling may sound gentle, but here it meant the difference between one kind of reality and another. In the hottest stages, the forces of nature may not have behaved in the separate ways we recognize today. As the temperature fell, the familiar patterns of physics began to emerge. The weak nuclear interaction and electromagnetism, which behave differently in the present universe, became distinct as the universe settled into a cooler state. This kind of transition is not like ice forming from water, but the comparison gives a useful feeling for the idea. When conditions change, matter can reorganize itself according to different rules. One of the most important changes involved the Higgs field. In the present universe, this field is connected to why many particles have mass. In the extremely hot early universe, particles behaved as if this mass-giving structure had not yet taken the form we experience now. As the universe cooled, the Higgs field settled into its familiar state, and many particles acquired the masses associated with them today. This was not a mechanical switch being flipped somewhere. It was a change in the state of the whole universe. At the same time, the universe was filled with fundamental particles. There were quarks, which would later become locked inside protons and neutrons. There were leptons, including electrons and neutrinos. There were particles that carried forces, allowing interactions to occur. But these particles were not yet assembled into atoms or atomic nuclei. The universe was far too hot for that. Any early attempt at stable structure would have been broken apart almost immediately by the surrounding energy. Quarks are especially important in this early chapter. Today, quarks are never found freely in ordinary conditions. They are confined inside particles such as protons and neutrons. But in the very young universe, the temperature was so high that quarks and gluons existed in a freer, extremely hot state known as quark-gluon plasma. This was not a gas of tiny hard balls. It was a dense, strongly interacting state of matter where the building blocks of later atomic nuclei had not yet become locked into their familiar forms. As expansion continued and the universe cooled further, quarks became confined. They combined into heavier composite particles, including protons and neutrons. This was a crucial step toward matter as we know it, though atoms were still far away. A proton is one of the basic components of atomic nuclei, but at this time, there were no ordinary atoms, no chemistry, and no light moving freely through transparent space. The universe was still too energetic and crowded for that kind of calm structure. Another part of the story involves antimatter. For nearly every kind of matter particle, there is an antimatter counterpart. When matter and antimatter meet, they can destroy one another and produce energy. In the early universe, matter and antimatter were both present in enormous amounts, constantly being created and destroyed in interactions. If the universe had made exactly equal amounts of matter and antimatter and treated them in perfectly equal ways, almost everything might have vanished back into radiation. Yet a small excess of matter survived. The details of how that excess arose remain one of the major unsolved questions in physics, and we will return to that mystery later. For now, it is enough to understand that during the first fraction of a second, the balance between matter and antimatter was already becoming one of the most important facts in cosmic history. Neutrinos also belong to this early environment. They are extremely light particles that interact only weakly with other matter. In the hot young universe, they were part of the dense particle mixture, colliding and interacting more often than they do today. As the universe expanded and cooled, neutrinos eventually separated from the rest of the matter and radiation, streaming freely through space. They are still around today, incredibly numerous, passing through the universe almost unnoticed. Their quiet presence is another reminder that the earliest stages did not simply disappear. They left relics behind. The first fraction of a second was also a time when small differences mattered. The universe was remarkably uniform overall, but it was not perfectly featureless. Tiny variations in density and energy would later become important. Gravity would gradually amplify them, drawing matter into regions that were slightly denser than average. But at this early stage, those variations were only faint seeds, buried in a universe still too hot for stars or galaxies. Their full story belongs to a later chapter, but their existence shows how the future was already hidden inside the early state. What makes this period so difficult to imagine is the combination of extremes. The universe was incredibly hot, incredibly dense, and changing incredibly fast, yet it was also governed by rules. It was not random chaos in the ordinary sense. Particles interacted according to physical laws. Fields shifted state, symmetries changed, energy transformed. Expansion cooled the universe, and cooling allowed new possibilities to appear. The first fraction of a second was not a mess. It was a rapid sequence of physical transitions. This is one of the most beautiful ideas in cosmology. The calm structures we know today were not placed into the universe fully formed. They emerged. Protons and neutrons emerged from earlier particle states. Atoms emerged later from nuclei and electrons. Stars emerged later from clouds of gas. Galaxies emerged from small density differences growing under gravity. The universe became familiar by passing through stages that were once completely unfamiliar. And yet, the first fraction of a second was not simply a distant scientific curiosity. Everything around you depends on it. The stability of matter, the existence of particles with mass, the survival of more matter than antimatter, and the first seeds of cosmic structure all connect back to this early period. A quiet room today is built on events that happened when the universe was young beyond imagination. The softness of air, the solidity of a floor, and the warmth of a living body are late consequences of that first violent cooling. There is something calming in that thought. Even the universe, in its most intense beginning, did not remain in that state forever. It expanded, it cooled, it changed. From conditions too extreme for atoms, it slowly became a place where stars could shine and minds could wonder. So as you listen, you do not need to hold every particle or transition in detail. You can simply imagine the young universe becoming less fierce step by step as heat gave way to structure and intensity gave way to possibility. The day behind you can soften in the same direction. What feels crowded and restless can settle. What feels too bright can dim. And in the quiet, you can rest inside a universe that also learned over time how to become calm. Chapter 5. The Planck Era, where our physics goes quiet. The Planck Era is where the journey toward the beginning becomes both most exciting and most humbling, because it marks the point where our best tested physics can no longer speak with complete confidence. In the previous chapter, we entered the first fraction of a second, the universe filled with energy, particles, heat, and rapid transformation. But even that strange early world is not the deepest edge. If we continue moving backward in thought, past the stages where particles interact in ways we can partly describe, we approach a boundary so extreme that the usual rules begin to lose their clarity. This boundary is called the Planck Era. The name comes from the Planck scale, a set of natural limits built from the fundamental constants of nature. These are not limits in the sense of a wall or a rule that forbids curiosity. They are more like signposts telling us that familiar descriptions are being pushed into a region where they may no longer apply. At ordinary scales, we can often separate the universe into large things and small things. For large things, gravity dominates. For small things, quantum physics dominates. But near the Planck scale, this separation breaks down. The universe was so dense, so hot, and so compressed in energy that gravity and quantum behavior would both have mattered intensely at once. This is the core problem. Our best theory of gravity is general relativity. It describes space and time as a flexible geometry shaped by matter and energy. It explains the motion of planets, the bending of light, the expansion of the universe, and the strange regions around black holes with remarkable success. Our best theory of the tiny world is quantum physics. It describes particles, fields, uncertainty, and the behavior of matter and energy at very small scales with remarkable success. Each theory works beautifully in its own domain, but the Planck era demands both at the same time. That is where physics becomes quiet, not silent because there is nothing to say, but quiet because certainty becomes difficult. When gravity becomes quantum, we need a theory of quantum gravity, a framework that can describe space-time itself under conditions where it may fluctuate, bend, and behave in ways that do not fit our ordinary picture. Many ideas have been explored. Some imagine space-time as having a deeper quantum structure. Some suggest that the beginning may not have been a singular point, but a transition. Some propose that the universe may have passed through a state where the usual meaning of time becomes blurred. These ideas are serious attempts to understand the boundary, but none has yet become a complete and confirmed description of the Planck era. This does not mean that the Planck era is fantasy. It means we are looking at a real scientific frontier. The reason scientists speak about it all is that our existing theories point toward it. When we trace cosmic expansion backward, density and temperature rise. When those conditions become extreme enough, the simple use of general relativity alone leads toward a singularity, a place in the mathematics where density and curvature become infinite. But infinity in a physical equation often signals that the theory is no longer enough. It is not always a discovery of something truly infinite in nature. Sometimes it is the theory telling us that a missing layer of physics is needed. A helpful comparison is the center of a black hole. General relativity predicts a singularity there too, but most physicists suspect that a complete theory of quantum gravity would change the story before a true physical infinity appears. The same may be true for the earliest universe. The Planck era may be the place where the smooth fabric of space-time, so useful in describing the cosmos today, gives way to something deeper. To picture this, imagine standing far away from the ocean. From a distance, the surface looks smooth. Waves rise and fall, but the water appears continuous. Now imagine zooming closer and closer, beyond waves, beyond ripples, down to the level where the smooth surface is revealed to be made of molecules. The old description was not wrong. It was simply incomplete at smaller scales. Space-time may be similar. At human scales, and even at the scale of galaxies, it can be treated as smooth. But near the Planck scale, the smoothness of space-time may no longer be the right picture. The geometry itself may have a quantum character. We should be careful with this image because no one has directly observed space-time at the Planck scale. It is far beyond the reach of current experiments. Still, the idea helps us understand why the usual question, what happened at the very first instant, may be harder than it sounds. If time itself is part of space-time, and space-time is undergoing quantum behavior, then time may not behave like a simple line that can be followed backward without end. The very idea of a first instant might need to be replaced by something more subtle. This is one reason the Planck era is so important for a journey to the beginning of time. It is not merely an earlier chapter in the same story. It may be the point where the book changes language. Before this boundary, if the word before even applies, the universe may not be describable by the same concepts we use afterward. Cause and effect, duration, distance, and geometry may all need deeper definitions. We can still ask questions, but we must ask them carefully. The Planck era also reminds us that science is not weakened by uncertainty. In fact, uncertainty is one of its strengths. A weak story pretends to know everything. A strong scientific picture identifies exactly where knowledge is firm and where it becomes incomplete. Scientists can describe later stages of the early universe with increasing confidence because those stages leave observable traces. But the Planck era is different. Its direct signals, if any survived, are difficult to separate from everything that happened later. The universe may carry clues, but they are faint, indirect, and challenging to interpret. There may be traces in the large-scale structure of the universe, in patterns from the earliest radiation, or in subtle gravitational signals from the young cosmos. But such clues are not simple messages. They must be measured with great care and compared with precise models. A signal from the Planck era would be one of the most important discoveries in the history of science. But for now, this remains a search rather than a conclusion. Because of this, the most honest description of the Planck era is a boundary between knowledge and mystery. On one side, we have a universe that can be described as hot, dense, expanding, cooling, and changing through known physical processes. On the other side, we have a region where the rules themselves may need to be reimagined. Not abandoned, but deepened. The Planck era does not erase physics. It asks physics to grow. There is something beautiful in that. The universe is not refusing to be understood. It is showing us that understanding has layers. At first, humans learned the motions of the sun and moon. Then they learned gravity, atoms, light, relativity, and quantum fields. Each step did not make the previous world meaningless. It revealed a wider one beneath it. The Planck era may be another such step, a hidden layer beneath space-time itself. For the listener, this may sound impossibly abstract, but the meaning can be simple. The beginning of time is difficult not because scientists lack imagination, and not because the universe is chaotic beyond reason. It is difficult because the beginning brings together everything we know into one extreme question. What is space when space itself is young? What is time when time is part of the thing being born? What is gravity when the geometry it shapes must also obey quantum rules? These questions do not yet have final answers, but they are not empty questions. They guide research, shape theories, and remind us that the universe is deeper than the familiar surfaces of everyday life. The floor beneath you, the air around you, the stars beyond Earth, and the galaxies beyond sight all exist within space-time. The Planck era asks what space-time itself is made of, or whether made of is even the right phrase. As we rest near this boundary, it is important not to turn mystery into fear. The quietness of physics here is not a darkness that threatens us. It is more like the hush at the edge of a forest before dawn, where shapes are present but not yet clear. Something is there, something real. We just do not yet have enough light to see it fully. And perhaps that is a gentle thought for the end of the day. Not everything has to be solved to be meaningful. Not every question has to become an answer tonight. The universe itself carries mysteries patiently, without hurry, and you can do the same. For now, let the mind soften at the edge of knowing and rest in the quiet space where even physics pauses. Chapter 6. Cosmic Inflation, when space expanded almost instantly. Cosmic inflation is one of the strangest and most powerful ideas in modern cosmology because it suggests that the universe became vast not slowly, but through a breathtaking burst of expansion before ordinary cosmic history truly settled into place. In the previous chapter, we reached the edge where known physics becomes uncertain. The Planck era asks what happens when gravity and quantum behavior must be understood together, and where the familiar meaning of space and time may begin to blur. Cosmic inflation belongs just beyond that deepest uncertainty, in a stage where scientists can build clearer models, but where important questions still remain open. It is not a fully proven event in every detail. It is a leading explanation for several remarkable features of the universe we observe today. The basic idea is simple to state, even if the physics behind it is profound. Very early in cosmic history, space may have expanded at an extraordinary rate. Not matter flying through space and not galaxies racing apart, because galaxies did not yet exist. Instead, the scale of space itself increased enormously in a tiny fraction of a second. Regions that were once extremely close together became separated by distances so large that they would later become far beyond one another's view. This rapid expansion is called inflation because the universe is imagined as swelling dramatically, like a surface being stretched far faster than ordinary expansion would allow. But the comparison should be used gently. The universe was not a balloon expanding into a room. The point is that distances inside space grew tremendously. The fabric of space did not need an outside place to move into. It was the internal scale of the universe that changed. One reason inflation is so important is that it helps explain why the universe is so smooth on very large scales. When scientists look at the ancient afterglow of the early universe, they find that it is almost the same temperature in every direction, with only tiny variations. This is surprising. Without inflation, regions on opposite sides of the observable universe seem too far apart to have exchanged heat or information in the early hot universe. They should not have had enough time to come into such close agreement. Yet they appear deeply coordinated. Inflation offers a solution. Before inflation, the region that would become our observable universe may have been small enough for its parts to influence one another and reach a shared condition. Then inflation stretched that region to cosmic size. What now appears as widely separated parts of the sky may have once belonged to a much smaller connected patch. The smoothness we see today could therefore be the stretched memory of an earlier closeness. Inflation also helps explain why space appears so close to flat on large scales. In this context, flat does not mean thin like a sheet of paper. It means that the geometry of space behaves, within our measurements, very much like ordinary geometry across enormous distances. Parallel lines remain nearly parallel. Triangles would have angles adding up in the familiar way, at least to the precision we can observe. General relativity allows space to have curvature, so it is natural to ask why the universe seems so close to flat rather than strongly curved. A useful analogy is a small patch on the surface of Earth. Up close, the ground beneath your feet can look flat, even though Earth is curved overall. If you could stretch a curved surface enormously, any small visible region would appear flatter and flatter. Inflation works in a related way. By stretching space so dramatically, it can make the observable region appear very close to flat, even if the full geometry of the universe is more complicated. There is another puzzle inflation may help with. Some theories of the early universe suggest that extremely heavy relic particles or strange defects in fields could have formed during early transitions. If too many of these remained, they might dominate the universe in ways we do not observe. Inflation would dilute such relics by stretching space so much that their density would become extremely small in the region we can see. In this way, inflation can act like a cosmic clearing process, leaving behind a universe that is smooth, flat, and free of certain unwanted leftovers. But what could cause such expansion? The most common idea is that inflation was driven by a special form of energy associated with a field filling space. In physics, a field is something that has a value throughout space, like the electromagnetic field or the Higgs field. During inflation, a field may have occupied a high-energy state with an unusual property. Instead of slowing expansion through ordinary gravity, it caused expansion to accelerate. The details depend on the model, and the exact identity of this field is not known. It is often called the inflaton, but that name is a placeholder for a deeper physical mechanism still under investigation. This is important because inflation is not simply fast expansion added by hand. It is an attempt to connect the early behavior of space to a physical source. The energy driving inflation would have shaped how quickly expansion happened, how long it continued, and how it ended. Different models make different predictions about the traces inflation might leave behind. Some are already disfavored by observations. Others remain possible. The search is not only for the idea of inflation, but for the specific physics behind it. Inflation could not continue forever in our region if the universe was to become the hot, particle-filled cosmos described in earlier chapters. At some point, inflation had to end. When it ended, the energy that had driven the rapid expansion would have been transformed into ordinary particles and radiation. This stage is often called reheating. It is not heating in the everyday sense of warming soup on a stove. It means the universe became filled with energetic particles again, setting up the hot, dense conditions from which later cosmic evolution could proceed. This connection matters. Inflation does not replace the hot early universe. Instead, it may explain what prepared it. The hot expanding universe of particles, radiation, cooling, nuclei, atoms, stars, and galaxies may have emerged after inflation ended. In that sense, inflation is like a hidden prelude. It shaped the stage before the familiar cosmic story began. One of the most beautiful aspects of inflation is that it may also explain where the first tiny irregularities came from. A perfectly smooth universe would never form galaxies. Matter would remain evenly spread with no slightly denser regions for gravity to gather. But our universe was not perfectly smooth. It had small differences, and those differences became the seeds of structure. During inflation, quantum fluctuations, tiny variations that naturally occur in fields, could have been stretched to enormous scales. After inflation ended, those stretched variations became differences in density. Over time, gravity amplified them, and they eventually helped form the cosmic web of galaxies. We will explore that process more deeply in the next chapter. But inflation provides the bridge between the tiny quantum world and the vast architecture of the cosmos. This is why inflation is so remarkable. It takes something microscopic and connects it to something larger than galaxies. It suggests that the largest structures in the universe may have roots in quantum behavior during an early burst of expansion. The quiet patterns observed across the sky may be traces of events that happened when the universe was younger than imagination can easily hold. Still, scientific honesty matters. Inflation is a powerful and widely studied idea, but the exact mechanism has not been confirmed. Scientists continue to test it through observations of the ancient radiation, the distribution of galaxies, and possible gravitational waves from the early universe. Some predicted signals have not yet been found. Some measurements support the general inflationary picture, while still leaving many versions of it possible. A good scientific story does not become weaker because it is tested. It becomes clearer as some possibilities survive and others fade. There is also a subtle point about speed. People sometimes hear that inflation expanded space faster than light, and imagine that this breaks the rules of relativity. It does not. Relativity says that objects cannot move through local space faster than light. But the expansion of space itself is different from ordinary motion through space. Very distant regions can become separated faster than light because the space between them is growing. No signal or object is outracing light through its local surroundings. In this way, inflation asks us to expand not only our picture of the universe, but our picture of expansion itself. Space is not a passive emptiness. It has behavior. It can stretch. It can carry light into longer wavelengths. It can preserve ancient patterns across immense distances. And, in the inflationary picture, it may once have grown with a speed and intensity that shaped everything that followed. For tonight, there is something calming in the thought that even the largest universe may have unfolded from a tiny connected beginning. Vastness does not always arrive all at once in a way we can understand. Sometimes it emerges from hidden conditions, quietly leaving traces that can be read much later. So let the mind rest with that image, space stretching, the early universe smoothing, the seeds of future galaxies being gently carried outward into the dark. Nothing in you needs to hurry. The cosmos itself took its time becoming clear. Chapter 7: Tiny Quantum Fluctuations That Became Galaxies. Every galaxy in the sky, from the Milky Way to the faintest distant smudge of light, may trace its ancestry back to tiny quantum fluctuations in the earliest universe. This is one of the most astonishing ideas in cosmology. The largest structures we know, vast collections of stars, gas, dust, dark matter, and black holes, may have begun as almost unimaginably small variations in energy. These variations were not galaxies in miniature. They were not little clumps of matter waiting to grow. They were slight differences in the early universe, tiny departures from perfect smoothness, stretched across space and later amplified by gravity. To understand why this matters, imagine a universe that is perfectly uniform. Every region has exactly the same density, exactly the same temperature, and exactly the same distribution of matter and radiation. Such a universe might expand and cool, but it would have no preferred places where structure could begin. Gravity would pull equally in all directions. No region would be slightly heavier than another. There would be no first clouds, no first stars, no galaxies, no planets, and eventually no quiet observer wondering about the beginning. Our universe was not perfectly smooth. It was almost smooth, but not completely. That small imperfection made everything possible. Across the ancient universe, there were tiny differences in density, so faint that they were only small ripples in an otherwise even cosmic sea. Yet gravity is patient. Give it enough time, and the smallest excess can become the beginning of something enormous. The source of these ripples is thought to lie in quantum physics. In the quantum world, fields are never perfectly still. Even in what seems like emptiness, they have small fluctuations. This does not mean the universe was messy or magical. It means that at the deepest level, physical fields have unavoidable uncertainty and activity. During cosmic inflation, as space expanded extremely rapidly, these tiny fluctuations could have been stretched from microscopic scales to cosmic scales. What began as quantum variation became written into the large-scale fabric of the universe. This is a delicate idea. because quantum fluctuations are not tiny grains floating in space. They are variations in fields, and fields are the basic language of modern particle physics. A field can fill all of space, and particles can be understood as excitations of fields. In the early universe, fluctuations in these fields affected the density and energy of different regions. When inflation stretched space, those fluctuations were carried outward and enlarged beyond ordinary imagination. After inflation ended, the universe became hot and filled with particles and radiation. The stretched fluctuations remained as tiny differences in density. Some regions were slightly denser than average, others were slightly less dense. The differences were extremely small, but they mattered because gravity responds to density. A slightly denser region pulls a little more strongly than its surroundings. Over time, that region can attract more matter, becoming denser still. This is called gravitational growth, and it is one of the main ways the universe turns simplicity into structure. In the very early hot universe, ordinary matter could not yet collapse freely into stars or galaxies. It was tightly connected to radiation. Electrons, atomic nuclei, and light interacted constantly, forming a hot plasma rather than calm neutral gas. Radiation pressure resisted collapse, pushing back against gravity. In this era, the universe behaved partly like a vibrating fluid. Regions of slightly higher density tried to fall inward under gravity, while pressure from radiation pushed outward. This produced waves in the early cosmic material, somewhat like sound waves moving through a dense medium, though not sound in the everyday sense of air carrying noise to an ear. Those early waves left a pattern. Later, when the universe cooled enough for neutral atoms to form, light separated from matter and began traveling freely. The ancient radiation from that moment still fills the universe today as a faint microwave glow. It carries a map of the early fluctuations, showing tiny temperature differences across the sky. These differences are not random decorations. They are the fossil imprint of the seeds from which structure grew. Dark matter played a crucial role in this story. Ordinary matter was held back for a long time by its interaction with radiation. But dark matter does not interact with light in the same way. It responds strongly to gravity, but it does not scatter photons like ordinary charged particles do. Because of this, dark matter could begin gathering into broad gravitational wells earlier than ordinary matter could collapse efficiently. Later, when ordinary matter became neutral and light moved freely, gas could fall into these dark matter wells. In this sense, dark matter helped provide an invisible scaffolding for the visible universe. The word scaffolding is useful, but it should not be taken too literally. Dark matter was not a rigid structure holding galaxies like beads on wires. It was a distribution of mass shaped by gravity. Slightly denser dark matter regions attracted more dark matter and eventually ordinary matter as well. Over long cosmic times, this produced a web-like structure. Dense knots, connecting filaments, sheets, and enormous voids. Galaxies formed preferentially in the denser regions, while the emptier regions became the great cosmic voids we see in large surveys of the universe. This process did not happen quickly. The fluctuations were tiny at first. They needed time. After the universe became transparent, matter continued to fall into gravitational wells. Gas collected, cooled, and eventually formed the first stars. These first stars were not arranged like the mature galaxies we see today. They formed in early clumps and small halos of dark matter. Over time, these clumps merged. Larger systems formed from smaller ones. Galaxies grew by gathering gas, forming stars, colliding with other galaxies, and being shaped by dark matter halos around them. The Milky Way itself is part of this long process. It did not appear fully formed. It grew through the slow assembly of matter across cosmic history. Some of its stars were born inside it. Others may have come from smaller systems that merged with it. Its spiral arms, central bulge, halo, gas clouds, and dark matter environment all belong to a story that began with those early fluctuations. When we say that tiny quantum fluctuations became galaxies, we do not mean they transformed directly and simply. We mean they created the first unevenness that gravity could work with. The beauty of this idea is that it connects two extremes that seem almost impossible to place in the same sentence. Quantum physics belongs to the smallest scales of nature. Galaxies belong to the largest visible structures. Yet the early universe may have linked them. Inflation stretched microscopic fluctuations across vast distances. Gravity then spent cosmic time turning those slight differences into the architecture of the universe. The smallest uncertainty became the beginning of the largest patterns. There is also a quiet precision in this story. The universe could not have had fluctuations that were too large, at least not if it was to resemble the cosmos we know. If the early differences had been much stronger, matter might have collapsed too violently and too early, perhaps producing a universe dominated by black holes or extreme clumps. If the differences had been much weaker, galaxies may not have formed efficiently at all. Our universe seems to have had just enough variation for structure to grow while still remaining smooth on the largest scales. This does not mean the universe was designed for us. Science does not need to make that claim. It means that the measured properties of the early universe allowed a particular history to unfold. Smoothness gave the universe large-scale order. Small irregularities gave gravity something to build. The result was a cosmos that could become rich without becoming instantly chaotic. The same pattern appears again and again in nature. A tiny difference can become important if conditions allow it to grow. A slight slope directs water. A small seed becomes a tree. A faint imbalance in a cloud can become a star. In the early universe, the differences were far smaller and the setting far grander, but the principle is related. Structure begins where perfect sameness is gently broken. When astronomers map galaxies across immense distances, they are not merely making a catalog of objects. They are reading the mature form of an ancient pattern. The positions of galaxies, the empty spaces between them, and the thread-like cosmic web all carry memory of the early fluctuations. The universe today is not disconnected from its beginning. It is the beginning, unfolded through time. Even the darkness between galaxies is part of the pattern. Voids are not failures of structure. They are the less dense regions that were left behind as matter flowed toward denser places. In a sense, galaxies and voids were born together. The universe became a web because gravity made some regions richer while others became emptier. Light gathers in the knots, but the silence around them also tells the story. For tonight, this thought can be held softly. The universe did not need to begin with finished stars or ready-made worlds. It began with subtle differences, almost hidden in the early heat, and gave them time to grow. Something nearly invisible became the galaxies. Something almost perfectly smooth became a sky full of structure. And perhaps that can let the day loosen its grip a little. Not everything meaningful begins loudly. Some things begin as the faintest ripple, almost too small to notice, and unfold slowly into something vast. You can rest now inside that same patient universe, where even the smallest beginnings are allowed time to become. Chapter 8. Matter wins by the smallest margin. The universe exists as a place of atoms, stars, planets, and living bodies because in its earliest moments, matter survived by a margin so small that it almost feels impossible. This chapter begins with a strange fact. In the deepest rules of particle physics, matter is not alone. For many kinds of matter-particle, there is an antimatter counterpart. An electron has an opposite partner called a positron. A proton has an antiproton. More generally, matter and antimatter can be thought of as mirror partners with opposite charges and related properties. They are not science fiction, and they are not imaginary. Antimatter is real. It can be produced in energetic particle collisions, it appears in some radioactive processes, and tiny amounts pass through nature in cosmic rays and high-energy events. But antimatter has a dramatic property. When a matter particle meets its antimatter counterpart, the two can annihilate. They do not simply break apart like ordinary objects. Their mass can be converted into energy, often in the form of energetic light and other particles. In ordinary life, this is rare because antimatter is scarce around us. But in the early universe, when temperatures were extraordinarily high, matter and antimatter were created and destroyed constantly. The young cosmos was not yet a quiet place of stable atoms. It was a searing particle environment where energy could become particle pairs, and particle pairs could return to energy. If the universe had created exactly equal amounts of matter and antimatter, and if both had behaved in a perfectly balanced way, the result would have been very different from the universe we know. As the universe expanded and cooled, matter and antimatter would have met and annihilated. Almost all of both would have disappeared into radiation. There might have been light, motion, and energy, but almost no leftover ordinary matter to form stars, planets, oceans, rocks, or bodies. There would be no atoms in the familiar sense, no chemistry, and no later structures like the Milky Way. And yet, here we are. The observable universe is filled mostly with matter, not antimatter. Galaxies, stars, gas clouds, planets, dust, and living things are made of matter. Antimatter exists, but only in small amounts under special conditions. This means that somewhere in the earliest history of the universe, matter gained the slightest advantage. The imbalance was tiny, perhaps roughly one extra matter particle for every billion matter-antimatter pairs. But after the pairs annihilated, that tiny excess remained. Everything built from ordinary matter may be the leftover trace of that small victory. This is why the phrase "matter wins" is so powerful. It does not mean matter defeated antimatter in a battle. It means that the laws and conditions of the early universe allowed a tiny surplus of matter to survive. That surplus became the raw material for cosmic history. After the Great Annihilation, the remaining matter could continue through later stages. It could become protons and neutrons, then simple atomic nuclei, then atoms, then gas clouds, then stars, then the heavier elements made inside stars, and eventually planets and life. The mystery is that our known physics does not yet fully explain how the imbalance became large enough. The universe clearly contains far more matter than antimatter today, but the exact process that produced this asymmetry remains one of the major open questions in cosmology and particle physics. Scientists have strong clues about what must have happened, but not a complete confirmed mechanism. For matter to gain an advantage, the early universe needed processes that treated matter and antimatter slightly differently. If every reaction involving matter had been mirrored perfectly by an equal antimatter reaction, no lasting imbalance could grow. The universe also needed ways to change the number of matter particles relative to antimatter particles. And the early universe had to be in a state where the usual balance of reactions could be pushed out of perfect equilibrium. In simple terms, there had to be a direction to the change, not just a constant back and forth that erased every difference as soon as it appeared. One key clue comes from a subtle imperfection known as charge parity violation. This means that some particle processes do not behave exactly the same when matter is exchanged for antimatter and spatial directions are mirrored. The effect has been observed in certain particle systems, so nature does allow small differences between matter and antimatter behavior. But the amount seen in known processes does not seem strong enough by itself to explain the full matter dominance of the universe. This suggests that there may be additional sources of imbalance still undiscovered, perhaps connected to particles or interactions beyond the familiar framework of particle physics. Neutrinos may be part of the story. These extremely light particles are abundant, elusive, and unusual. They come in different types and can change from one type to another as they travel. Some theories suggest that neutrinos, or heavier relatives of neutrinos in the early universe, could help explain how a matter-antimatter imbalance developed. This idea remains under investigation. It is attractive because neutrinos already show that the particle world contains behavior that once seemed unexpected. But the connection to the cosmic matter surplus is not yet proven. There are also ideas involving new particles, new fields, or phase changes in the early universe. A phase change is a transition where the state of a system changes as conditions shift, like water freezing into ice, though the early universe versions would be far more fundamental. As the universe cooled, fields may have settled into new states, and during such transitions, matter and antimatter might have been affected differently. These possibilities are studied because the early universe was not a calm laboratory. It was changing quickly, cooling rapidly, and moving through conditions that cannot be found naturally today. This is where scientific humility becomes essential. We should not pretend to know exactly how matter won. The evidence tells us that it did. The existence of galaxies and atoms is itself part of that evidence. Observations show a universe dominated by matter. The absence of widespread annihilation signals suggests that large nearby regions of antimatter are unlikely. If entire anti-galaxies were mixed into the observable universe near ordinary galaxies, their boundaries would likely produce energetic radiation where matter and antimatter met. We do not see such evidence on the required scale. This does not mean there could not be tiny amounts of antimatter here and there, or antimatter produced in specific high-energy processes. That certainly happens, but the large-scale universe we observe appears overwhelmingly made of matter. The question is not whether antimatter exists. It is why it did not survive in equal cosmic abundance. The answer may require physics not yet fully known. This is not a weakness in the story. It is part of what makes the story alive. The matter-antimatter problem sits at the meeting point of the smallest and largest scales. To understand why galaxies exist, we may need to understand tiny particle processes that happened when the universe was extremely young. The existence of a star can depend on an imbalance in the behavior of particles. The existence of a human hand, a breath, a memory, or a quiet room can be traced back to a difference so small that it almost vanished. There's a beautiful tension here. The universe is vast beyond ordinary imagination, but its future may have depended on a microscopic asymmetry. If the balance had been perfect, the cosmos might have become a bath of radiation with almost no matter left behind. Instead, there was a remainder. Not much compared with the enormous particle activity of the beginning, but enough to fill the universe with hydrogen and helium. Enough for gravity to gather gas into stars. Enough for stars to forge heavier elements. Enough for planets to form from those elements. Enough for chemistry to become complex. This also gives a deeper meaning to the word ordinary. Ordinary matter is not ordinary because it was guaranteed. It is ordinary only because it survived. The atoms around you are not the main bulk of what the early universe produced in its first hot reactions. They are the leftover excess after one of the greatest disappearances in cosmic history. Most matter and antimatter pairs annihilated. What remained became everything familiar. And yet, this is not a violent thought in the end. It is strangely gentle. The universe did not need a large victory for matter. It needed only the smallest margin. A faint imbalance, preserved through cooling and expansion, became the foundation of stars and worlds. The story of existence is not always the story of overwhelming force. Sometimes it is the story of what remains. So as this chapter settles, let the idea become quiet rather than heavy. You are made of the matter that endured, the small remainder that the early universe did not erase. The day may have felt full, loud, or uneven, but even a tiny remaining calm is enough to begin from. Tonight, you can rest as part of that ancient surplus, carried forward by a universe where the smallest difference became everything. Chapter 9. The First Light of the Universe. The first light of the universe is not only ancient radiation. It is the moment when the cosmos finally became transparent enough to let its own history travel freely across space. Before this moment, the universe was not dark in the ordinary sense. It was filled with light, but that light could not move far. The young universe was still a hot, dense plasma, a state of matter in which atomic nuclei and electrons were separated rather than joined into neutral atoms. Photons, the particles of light, were constantly scattered by free electrons. They tried to travel, but again and again they were redirected. The universe was bright everywhere, yet opaque, like a glowing fog with no clear view through it. This is a strange idea because we usually connect light with visibility. If something is bright, we expect it to reveal what is around it. But brightness alone is not enough. A thick cloud can glow from sunlight and still hide the landscape beyond it. A foggy street can be filled with light and still obscure the distance. The early universe was far more extreme than either example, but the principle is similar. Light existed, but it was trapped in constant interaction with matter. As the universe expanded, it cooled. This cooling did not simply make the cosmos less hot. It changed what matter could become. At very high temperatures, electrons moved too energetically to remain bound to atomic nuclei. Any forming atom would quickly be broken apart by the surrounding radiation. But after enough expansion, the temperature dropped to the point where electrons could join with nuclei and remain attached. Neutral atoms, mostly hydrogen with some helium, could finally exist in large numbers. This transition is often called recombination, though the name can be slightly confusing. It sounds as if electrons and nuclei were being reunited after having been together before. But in the early universe, they had not previously formed stable atoms in the ordinary way. The word remains because it describes electrons combining with nuclei into neutral atoms. What matters is the physical change. The universe went from a charged plasma to a mostly neutral gas. That change transformed the behavior of light. Free electrons are very effective at scattering photons. Neutral atoms, under those conditions, were much less effective at blocking the path of the radiation. Once electrons became bound inside atoms, photons could travel much farther without being scattered. The universe became transparent. Light that had been trapped in the glowing fog was released into open cosmic space. This released light is what we now call the cosmic microwave background. It is sometimes described as the oldest light we can observe. That does not mean no photons existed before it. Light existed earlier, but it could not travel freely enough to preserve a clear image of the universe. The cosmic microwave background is more like the first visible surface of the young cosmos, the earliest light that could begin a long journey across space and still reach us with information intact. When that light was released, it was not microwave radiation in the cold, faint form we detect today. It belonged to a much hotter universe and would have appeared as a warm glow. But space has expanded enormously since then. As the universe expands, the wavelength of traveling light stretches with it. Over cosmic time, that ancient glow was stretched from shorter wavelengths into microwaves. The light also became colder and weaker. Today it fills the universe as a faint background radiation, arriving from every direction in the sky. This is one of the most powerful pieces of evidence for the hot early universe. If the universe began in a hot, dense state and then expanded and cooled, it should have left behind a relic glow. That glow should be nearly uniform because the early universe was nearly uniform. It should be cooled and stretched by expansion. It should come from all directions, not from one star or one galaxy. This is exactly what is observed. The cosmic microwave background is not an object sitting somewhere in space. It is the afterglow of a stage the entire observable universe once passed through. But the cosmic microwave background is not perfectly smooth. It is almost smooth with tiny variations. Some regions are very slightly warmer and others very slightly cooler. These differences are small, but they are not meaningless. They show that the early universe had subtle differences in density and temperature. In the previous chapter, we explored how such small variations could become the seeds of galaxies. Here, the important point is that the first light preserved those variations like a delicate photograph of the young universe. The word photograph is helpful, but only if we use it carefully. The cosmic microwave background is not a photograph of objects like stars or planets. Those did not yet exist. It is a map of radiation from a time when the universe was becoming transparent. It shows conditions in the hot gas from which later structures would grow. When scientists study it, they are not seeing galaxies in baby form, but the early pattern from which galaxies would eventually develop. This is why the first light is such a turning point in cosmic history. Before transparency, the universe was difficult to observe directly because light could not carry a clean message from one place to another. After transparency, the universe entered a new phase. Radiation could stream freely through space. Matter, now mostly neutral, could begin responding more clearly to gravity. Over long periods, gas would fall into denser regions, stars would eventually ignite, and galaxies would slowly take shape. The first light also gives us a boundary to what ordinary light can show. Telescopes can look very far away, and therefore very far back in time, because light takes time to travel. But ordinary light cannot show us directly earlier than the transparent universe. If we try to look beyond the cosmic microwave background using light, we meet the glowing wall of the earlier plasma. It is not a wall made of solid material. It is a limit created by the fact that photons were constantly scattered before that time. The universe itself was not yet clear. This does not mean earlier times are unknowable. Scientists can study them indirectly through the patterns left in the cosmic microwave background, through the abundance of light elements, through the growth of large-scale structure, and perhaps through other messengers, such as gravitational waves or neutrinos. But the cosmic microwave background marks the earliest clear light-based image of the universe. It is the point where the cosmos becomes visible to itself. There is something deeply poetic about that. For a long time, the universe was bright but blind. Light existed everywhere, yet no beam could travel freely enough to reveal a distant view. Then, as expansion cooled the plasma into atoms, space opened, the fog lifted. The universe did not suddenly create light for the first time, but it allowed light to become a messenger. From that moment, radiation could carry memory. That memory has been traveling ever since. The photons of the cosmic microwave background have crossed expanding space for almost the entire age of the universe. They have passed through regions where galaxies later formed, through clusters and voids, through the changing gravitational landscape of cosmic time. They arrive now as faint microwave radiation, stretched and cooled, but still carrying information from the era when atoms first became stable. When we detect this light, we are receiving a message older than any star we can see with our eyes. The sun did not exist. The Milky Way did not exist in its present form. Earth did not exist. Heavy elements had not yet been forged in stars in the amounts needed for rocky planets and living bodies. The universe was simpler, hotter, smoother, and younger. Yet inside that simplicity were the conditions that would eventually lead to everything familiar. The first light also changes how we think about darkness. The darkness of space is not the absence of history. It is filled with a faint glow from the early universe, too cold and stretched for human eyes, but real. Every direction carries this ancient background. Behind the stars, behind the galaxies, beyond the visible shapes of the night sky, there is a soft relic of the moment when the cosmos became transparent. And so the first light is not merely a scientific signal. It is a horizon of vision. It is the oldest light that can reach us in a direct way. It tells us that the universe was once hotter, denser, and more uniform. It shows us that atoms formed only after the cosmos cooled. It preserves the tiny variations that later became structure. And it reminds us that seeing is itself part of cosmic history. The universe had to become transparent before it could be observed. For tonight, let that image become gentle. Imagine the early fog lifting, not suddenly or violently, but through cooling, settling, and release. Light begins to travel. Space becomes clear. A message starts crossing the universe quietly for ages beyond ordinary thought. And now, in this small moment of listening, you can let the day become transparent too, letting its noise scatter less and less until only a soft background calm remains. Chapter 10. what the beginning of time still hides. The beginning of time remains one of the rare places where science becomes both deeply precise and deeply unfinished. After traveling through the expanding universe, the early heat, the first particles, inflation, the seeds of galaxies, the survival of matter, and the first light, it may feel as if the story has reached a clear answer. We can describe a great deal. The universe expanded from a hotter and denser past. It cooled. Matter changed form. Light became free to travel. Gravity shaped tiny differences into stars and galaxies. The evidence for this broad history is strong. It is written into the motion of galaxies, the ancient background radiation, and the chemical simplicity of the early cosmos. And yet, the deepest beginning is still hidden. This is not because science has failed. It is because science has succeeded far enough to see exactly where the next mystery begins. The early universe can be traced backward through many stages, but as we approach the most extreme boundary, our familiar tools become incomplete. We can follow the story toward the edge, but the edge itself asks questions that current physics cannot yet answer with certainty. One of those questions is whether time truly began. In ordinary speech, we ask what happened before the Big Bang, as if the universe were a film and we simply want to rewind a little farther. But time may not work that way at the beginning. If time is part of the universe rather than a background outside it, then asking what happened before time began may be like asking for a place beyond the meaning of place. The question may still point toward something real, but the language we use may be too simple for the reality it tries to describe. This does not mean the word before is useless. In some models, the hot expanding universe may have emerged from an earlier state. There could have been a previous contracting phase, a cosmic bounce, or some deeper quantum condition from which our familiar spacetime arose. In such pictures, before can have a kind of meaning, though not always the same meaning it has in daily life. In other models, the beginning may be more like a boundary, where time does not extend backward in the usual way. At present, no single answer has been confirmed. Another hidden question concerns the nature of space-time itself. We experience space as the room in which things exist and time as the flow in which events unfold. But modern physics treats space and time as part of the physical structure of the universe. They can bend, stretch, and respond to energy. Near the beginning, that structure may have been so extreme that it cannot be treated as smooth in the ordinary way. A complete theory of quantum gravity would be needed to describe it fully, and that theory remains incomplete. This matters because the earliest universe brings together the largest and smallest questions at once. Gravity shapes the whole universe, but quantum physics governs the smallest scales. In most situations, scientists can use one description without needing the other in its most extreme form. Near the beginning, that separation disappears. Space, time, matter, energy, and quantum uncertainty all meet. The beginning of time may be the place where the universe asks for a deeper theory than any we currently possess. The singularity is part of this mystery. When the equations of general relativity are pushed backward far enough, they point toward a state where density and curvature become infinite. But scientists are cautious with this result. An infinity in an equation often signals that the theory has been stretched beyond its proper range. It may not mean that nature truly contained an infinite point. It may mean that new physics is required before we reach that conclusion. The singularity may be less like a physical object and more like a warning sign at the end of an unfinished map. Inflation also hides unresolved questions. It may explain why the universe appears smooth and nearly flat, and why tiny early fluctuations were stretched into the seeds of later structure. But what exactly drove inflation? What field or physical mechanism caused such rapid expansion? How did it begin? How did it end? And did it happen only in our region of the cosmos? These questions remain open. Inflation is a powerful framework, but its deepest engine has not yet been identified with certainty. There is also the question of whether our observable universe is all there is. We can see only as far as light and other signals have had time to reach us. Beyond that lies a cosmic horizon. There may be more universe beyond it, perhaps vastly more. It may be similar to what we see, or it may contain regions with different histories. Some versions of inflation even suggest that our observable universe could be one region inside a much larger structure. These ideas are fascinating, but they are difficult to test, and science must be careful not to confuse possibility with proof. The origin of matter remains another hidden chamber. We know that matter survived while antimatter became rare, but the complete reason is not yet known. The universe contains stars and planets because a tiny imbalance favored matter. Known physics contains hints of such imbalance, but not enough to fully explain the amount of matter we observe. This suggests that the earliest universe may have involved processes still unknown, perhaps involving particles or interactions not yet discovered. Dark matter adds another layer. It shaped the growth of galaxies, yet we still do not know what it is made of. We see its gravitational effects, but not its identity. Dark energy, the name given to whatever is driving the accelerated expansion of the universe, is even more mysterious. These ingredients belong more to the later universe than to the first instant, yet they remind us that the cosmic story is not complete. The beginning is hidden, partly because the present still contains unknowns. The first light of the universe gives us an extraordinary picture of the young cosmos, but even that picture has limits. It shows the universe after it became transparent, not the earliest moments themselves. Earlier than that, light was scattered constantly, and ordinary telescopes cannot see directly through the glowing plasma. To reach deeper, scientists must rely on indirect traces, patterns in the ancient radiation, the distribution of galaxies, the abundance of elements, and perhaps signals carried by gravitational waves or neutrinos. The universe may have preserved clues, but they are subtle and difficult to read. This is why the beginning of time remains a mystery of evidence, not mere imagination. It is not an empty space for any idea at all. Some possibilities fit observations better than others. Some are testable. Some are elegant but uncertain. Some may one day be ruled out. The mystery is disciplined. It is held in place by what the universe actually shows us. This is why the hidden beginning is not a license to believe anything without evidence. A good idea about the first moments must still connect to the universe we observe. It must respect the measured expansion, the ancient radiation, the formation of light elements, and the growth of cosmic structure. The beginning may be hidden, but it is not completely detached from observation. Like a footprint at the edge of a dark shore, the early universe left shapes that can still guide us. That discipline is what makes the unknown beautiful. Science does not need to turn every mystery into a quick answer. It can stand at the edge and say, here is what we know, here is why we know it, and here is where the darkness begins. The darkness is not failure. It is the next horizon. For a human life, the beginning of time may feel impossibly remote. It happened before Earth, before the sun, before the elements of your body were forged in stars. But it is not disconnected from you. Every atom around you belongs to the unfolding of that early history. Every breath depends on matter surviving, stars forming, heavy elements spreading, planets cooling, and life emerging. The hidden beginning is not just behind the universe, it is beneath the present moment. Perhaps the most honest ending to this journey is not certainty, but wonder. We know enough to see that the universe had a hot, dense, structured beginning to its observable story. We know enough to trace the path from early light to galaxies and stars. But we do not yet know why there is a universe, whether time had an absolute first edge, or what deeper laws shaped the earliest state. And that is all right. The universe does not become less meaningful because it still hides something. It becomes more spacious. The unanswered questions leave room for curiosity, patience, and awe. So tonight, let the mystery remain gentle. You do not have to reach the first moment or solve what came before it or understand the deepest structure of time. You can simply rest inside the story it made possible. The universe began, or became, or unfolded from something our physics has not yet fully named, and somehow that long unfolding has arrived here in this quiet breath, in this soft darkness, with nothing more required from you now than to let go. And now, my friend, our journey to the beginning of time has reached the edge of what science can clearly see. We followed the universe backward through expansion, heat, particles, inflation, the first seeds of galaxies, the survival of matter, and the first light that still whispers through space today. But the deepest beginning remains beautifully unfinished. Somewhere beyond our current theories, time itself becomes mysterious, and the universe still hides part of its first secret. If you're still awake and want to keep drifting through the cosmos, you can choose another quiet journey from the channel and let the next story carry you a little farther. But if sleep is already close, then let the questions fade for tonight. Thank you for being here, my friend. Rest well, let the day go, and sweet dreams among the stars.